Good evening, my dear students. At this particular time, 5:30 today, we will be discussing an important topic in 2 years physics by name electromagnetic induction. On an average, right from this chapter, one or sometimes two questions come. Definitely one question always come there. And there are good number of years. In the last 5 years, there are 3 years where they have given two questions. Okay. In order to do this topic, you need to have clarity about different parts of electricity. Some idea about electromagnetism, current electricity, magnetism, all these topics are required there. But generally, in NEET, they ask almost a straightforward question in electromagnetic induction. Since it is a combination of 3-4 chapters, they will be generally good enough, kind enough to give an easy bit, comparatively easy bit there. When once you are thorough with the basics and basic questions, you are almost likely to get the answer for the question. Okay. Now, under the heading of this electromagnetic induction, the first thing we need to understand is about magnetic flux there. Okay. Now, we want to understand how do we calculate magnetic flux linked with a coil. For example, this is a coil there. So you can see that this is the coil here having n number of turns. There's a turn number 1, turn number 2, like that n turns are there. Let us say radius of the coil is r. Okay, cross-sectional area of the coil comes out to be pi r square. So I repeat again, there is a coil with n number of turns. Each coil is of radius r and cross-section area of each turn of the coil is pi r square. Okay, this coil is kept in uniform magnetic field of induction B. The coil is kept in uniform magnetic field of induction B. Okay, there is a very important term about theta. Theta is said to be the angle between the magnetic field induction and area vector. What do you mean by area vector? All of you know that this is said to be the plane of the coil. Anything perpendicular to the plane of the coil is said to be the area vector. Okay, this is the plane of the coil. Perpendicular to this is the area vector there. So area vector will have magnitude equal to its area and the direction is perpendicular to its plane like this. The angle between A and B is nothing but theta. Theta is the angle between the area vector and B vector. Okay. So for the last time, I'm repeating the simple terminology we use there. The total number of turns in the coil is N. Area of each turn is A. The coil is kept in uniform magnetic field of induction B. And theta is the angle between A and B, area vector and magnetic field induction vector. With such a terminology, the flux linked with the coil, magnetic flux linked with the coil is given by BAN cos theta, BAN cos theta. Okay, I want to know what is the SI unit of magnetic flux. Under the heading of units and dimensions, they can ask a small bit. The SI unit and dimension formula of magnetic flux they can ask. Okay, magnetic field induction is in terms of Tesla, Weber by meter square. Area is meter square. Number of turns, no unit. Cos theta, no unit. So meter square get cancelled there. So naturally, SI unit of flux comes out to be Weber. Okay, so the point which we have to use frequently in this topic is magnetic flux linked with a coil that is given by BAN cos theta. Okay, now, what is the Faraday's law? Most of the subtopics in this particular chapter revolve around this Faraday's law. Faraday's law says that whenever the flux linked with the coil is changing, flux linked with the coil is changing with respect to time. As time changes, flux changes. Then some EMF is induced in the coil and current is induced in the coil. That particular EMF induced in the coil is given from Faraday's law as The EMF induced in the coil at any time t is given by minus d phi by dt. Okay, I repeat, whenever the magnetic flux linked with the coil is changing with respect to time, as time changes, flux changes, then some EMF is induced in the coil. That means the coil behaves as if it is a battery with some EMF being developed. And that EMF developed in the coil, induced in the coil at any time t is minus d phi by dt. Okay, what does the minus sign say, sir? Minus sign, according to Faraday's law and Lenz's statement, says that the EMF is induced in such a way so as to oppose the change in the flux. There is a reason for the flux to change. The EMF is developed in such a way to counteract, to oppose that particular change in the flux. Okay, that point is the fundamental point. So the EMF induced in the coil is minus d phi by dt. Okay, this will give you EMF induced in the coil at certain instant of time. So that is known as instantaneous EMF. EMF induced at one instant of time. Now, over a time interval, what is the average EMF induced? Okay, suppose I want EMF induced at 9th second, then that is instantaneous EMF. You have to go for differentiation. Suppose I want EMF developed during t is equal to 1 to t is equal to 5 seconds over a time interval, then the average EMF induced over a time interval delta t is given by minus of d phi by dt. What do you mean minus of delta phi by delta t? What do you mean by delta phi? Delta phi comes out to be phi 2 minus phi 1 and delta t is t2 minus t1. I repeat that phi 1 is the flux at t1 time, phi 2 is the flux at t2 time there. Then average EMF induced over a time interval delta t is minus of delta phi by delta t, minus of change in the flux phi 2 minus phi 1 by corresponding time interval t2 minus t1. So there is all likely chance that the question may be from a simple Faraday's law in the final entrance exam. Okay. Coming to the next point. Whenever EMF is induced in a coil, that particular coil is not a coil now. It is almost a battery. You know that every battery will develop the current there. Okay. Whenever a battery is there in a closed circuit, it definitely develops current. Whenever EMF is induced, some current is induced there. What is the current induced in the coil at any specific time t? Once again, the current induced in the coil at any specific time t is, you know the formula for our current from current electricity. Current is nothing but total EMF by total resistance there. So the current induced in the coil is EMF induced in the coil divided by resistance. So whatever EMF induced by resistance will give you the current. Okay, what is the EMF induced in the coil at any time t? Instantaneous EMF. That means d phi by dt. I have put the mod here, the mod. So mod of EMF induced under d phi by dt divided by corresponding resistance. Okay, now in what way the current, this dt term you are bringing here there. This dt term if you bring here there, I dt comes to be d phi by r, and I into dt is nothing but the charge is set into motion. The fundamental point, first point in current electricity is that current is developed whenever the charge is set into motion there. So current is rate of flow of charge dq by dt. This I dt is nothing but a charge that is set into motion. Okay, now I dt is nothing but charge set into motion that comes to be d phi by r. From the examination point of view there, this is another important equation there. In the entrance exam, you can just recollect that in any coil, if the flux is changing with respect to time, point number one, EMF is induced. In the closed loop, current is induced. For current to be induced, charged particles must be set into motion. How much charge should move for that current to be developed means that the charge to be set into motion is the change in the flux divided by corresponding resistance of the coil. Okay, very frequently touched point in the entrance. Okay, now other small point of current electricity, what we want is that suppose there is a current time graph. Whenever there is a current time graph, area enclosed by current time graph with respect to the time axis will give you the charge. Every one of you know area enclosed by IT graph with respect to time axis will give you charge. So one of the point we have to use as a fundamental point as we proceed further. Okay, the other relevant point is this particular one there. You must be knowing from electromagnetism. So your teacher has arranged all the required points at one place in order to understand the topic. One of the small points from electromagnetism is that suppose current is flowing through a coil in clockwise direction. Current is flowing through a coil in clockwise direction. Then using the right hand thumb rule, we can show that the inward magnetic field is developed. If the current is in anti-clockwise direction, outward magnetic field is developed. These are the small points from electromagnetism, fundamental points there. So these things we have to repeatedly use, please. Okay. Now we are going to have the application of some problems which can be expected in the coming NEET. Okay, before that, another requirement is there. We need to know differentiation. Already you're thorough with differentiation there. Differentiation of t cube with respect to t, 3t square. So differentiation of t square with respect to t, 2t. All these formulas we have to repeatedly use even in this particular topic. Okay then, see here. Now, the first important question as well as the answer right here, there, just go through it. The magnetic flux, the symbol for magnetic flux is phi. Magnetic flux passing perpendicular to the plane of the coil is given by phi is equal to t cube plus 4t square plus 12 Weber. Magnetic flux is t cube plus 4t square plus 12 Weber, where t is in second. I want to know what is the current induced at t is 4 seconds. I want current induced at specific time. That means I want to know what is the instantaneous current. What is the current instantaneous at some instant? Current at one specific instant like 4 seconds. I want the specific current at that time, that is known as instantaneous current there. I want what is the instantaneous current developed at t is equal to 4 seconds. Not only I want magnitude of current, I want direction of current, both magnitude and direction. Okay, this is a diagram given, and right in the diagram, you can see the overall resistance of the loop is also given, 8 ohms. That's the resistance of the loop. Point number 1. As every one of us know, time will never wait for anyone there. Time keeps on going ahead there. Okay, 5:30, 6:30, 7:30. Here, time keeps on changing. As time changes, flux changes. What does the Faraday's law say? Whenever flux changes with respect to time, some EMF is induced. Fundamental point number 1. Point number 2. If it is a closed loop, current is inevitably established. Yes, 100% it is a closed loop. Current is established. I want to know current in magnitude as well as in direction. Okay, so flux is t cube plus 4t square plus 12 Weber. Whatever I said, I have written here there, please. Time keeps on increasing. Upward arrow mark says increase. As time increases, flux increase. Now you ask, what type of flux is increasing there? This is a symbolic representation of inward flux. There's a symbolic representation of inward flux. So as time increases, this inward flux is increasing. Okay, now whenever the flux, I will come back to the other points after half minute there. Then whenever the flux changes with respect to time, some EMF is being induced. Okay, I want the instantaneous EMF induced at t is 4 seconds. Instantaneous, not average. Okay, what the EMF induced at any instant of time means? Whenever you want instantaneous values, you have to go for differentiation. So EMF induced is d phi by dt. Already we know differentiation of t cube comes to be 3t square. Differentiation of t square is 2t. 2t into 4 is 8t. Differentiation of this pure number is 0. So what the EMF induced means? 3t square plus 8t. I want to know what the EMF induced at t is 4 seconds. What the EMF induced at t is 4 seconds means in place of t, you just write 4. So EMF induced is 3 into 4 square plus 8 into 4. It comes out to be 80 volts. So exactly at 4th second, this much EMF is being induced in the coil. My God, it becomes almost something like a ready powerful battery of 80 volts. Okay, this is the EMF that is being developed there. Now I want to know what is the corresponding current there. Current is EMF by resistance there. EMF is 80. You just observe resistance given in the diagram there. It is not mentioned in the question part given in the diagram. Wherever it is, that's the data you have to use, 8, 10 ampere. So the current magnitude is 10. What about the direction? Okay, what about direction? Is this current in this loop flow clockwise or anti-clockwise? Okay, we are revisiting the point where we stopped intentionally. You know that as time increases, flux increases. What type of flux? Here the flux or field are given in the inward direction. The inward field, inward magnetic field, inward flux is increasing. Okay, inward magnetic field is increasing. It doesn't like the inward magnetic field to increase. As per Lenz's law, it tries to oppose the change. Basically, the inward magnetic field is increasing. That is responsible to give the EMF there. It wants to oppose that basic cause. That root cause, it wants to oppose. The root cause is inward magnetic field is increasing. It doesn't like it. So it wants to develop outward field there. It wants to develop outward one. Okay. Now, in order to get the outward current there, in order to obtain outward magnetic field, current should go in anti-clockwise direction. Okay, if the current goes anti-clockwise, then only field will be outward there. Outward can be established only by anti-clockwise current. Now, if you happen to see here there, the inward B is increasing, so it has to develop outward. Then, as per Lenz's law, to develop outward there, the current has to go in anti-clockwise. In a hurry, you should not answer just by seeing the magnitude of 10. 10 ampere clockwise or 10 ampere anti-clockwise. Both the statements you have to see and then pick up the correct option, please. Then, this is a question where we will be differentiating twice. Listen carefully. Particularly in this particular topic, the differentiation plays a vital role in most of the PYQs there. Most of the PYQs. Okay, for example, there's a chapter by name Mechanical Properties of Solids or Surface Tension or Fluid Mechanics. Almost nowhere you use differentiation, almost nowhere. But here we need to use frequently. That's why the list of differentiation formula are given and we will be using it. Now, the magnetic flux passing through a metallic ring varies with time t as the flux is given as 60 cube minus 18 t square. Okay, there's a question, there's an answer there, flux is given. Now, the resistance of the coil is given as 3 ohms. Very good. I want to know at what instant of time there, what is the time t where the current induced is maximum. He is not asking what is the current induced at so and so time. Instead, he is asking at what time, whatever current is induced, that current reaches its peak value there. Once again, I repeat, as flux changes, EMF is developed. As EMF is developed, current is developed. Here, most probably, that current would have been varying current. That varying current touches the ultimate value, highest value at one time. He is asking what is the time at which the current attains its maximum value. Not a difficult question, friends. Not at all. Okay? Then keep in view the possible little bit of extra standard they have to maintain in the NEET. Then this question finds our discussion there. Flux is given as 60 cube minus 18t square. I want to know what is the EMF developed there. The EMF developed is nothing but, I want mod of EMF. Okay, mod of d phi by dt. So what is d phi by dt? You have to differentiate it. 6 as it is. Differentiation of t cube is 3t square. 18 as it is. Differentiation of t square is 2t. If you simplify, 18t square minus 36t. This is a EMF induced. Already we had done differentiation once, please. Okay, then I want to know what is the current developed there. Current developed is total EMF by total resistance, small point from current electricity. So EMF induced is this much. Resistance is given as 3 ohms there. So if you simplify there, 18 by 3, 60 square minus 12t. This is a current developed. By now, you can make a note that this current is a function of time. As time changes, current is going to change. At one particular time, this current is going to be maximum. I want to know at what time the current is maximum. That's a question. That's a question. Okay. If they go for new bit, which is slightly difficult, not too much difficult, slightly difficult, then this question suit all their requirements. Now, the current is 60 square minus 12t. I want the current is maximum. Only one small point you have to know in different topics of physics. When, for example, current is maximum means its a differentiation value, di by dt should be equated to 0. Okay, when current has to be when, for example, force is maximum, df by dt is 0. Momentum maximum, dp by dt is 0. Current maximum, di by dt is to be 0. So you have to do differentiation for the second time. So current is given as 60 square minus 12t. Now we want to know di by dt. What is di by dt? You have to differentiate it. 6 into differentiation of t square is 2t. So that's why 12t. 12 into differentiation of t is 1. So 12t minus 12. So if you differentiate I with respect to t, this comes to be this one. For current to be maximum, di by dt has to be 0. So equate di by dt, nothing but this to 0. 12t minus 12 is 0. That means 12t is 12 and t is 1 second. Exactly at 1 second. Whatever current that is being established in the coil reaches the maximum value. In the form of statements they can give there. Instead of asking like this, the option 1 they can give from 0 to 1 second current increase, and 1 thereafter, and after 1 second current decrease. Is current is maximum at 1 second. So 0 to 1 current increase, thereafter current decrease. There's a correct answer for the bit. Okay. While explaining, also focus, sir. Okay, while explaining. Yeah. My dear students, yeah, another good application of Faraday's law. A coil of radius r, it is a letter notation question. So the main letters should go to the brain directly, that I have highlighted. A coil of radius r having n number of turns is placed perpendicular to the magnetic field. Resistance of the coil is given as R. Power dissipated is given as P. I want to know what is the rate at which magnetic field is changing. Okay. First of all, we want to know rate of change of magnetic field. What do you mean by rate of change of magnetic field? Means dB divided by dt. All of you know rate of change of momentum, dP by dt. Rate of change of magnetic field, nothing but dB by dt. We want to know what is dB by dt. Okay, once again I repeat, what are the things given? What are given the question means the radius given, radius of the coil, number of turns, the resistance of the coil, capital R given, and power dissipated is given as P. From this, we want to calculate dB by dt. Okay. In the NTA conducted entrances there, this particular question, numerically once they have given, letter notation they have given, and so on. Okay. Once again, we started our discussion like this. What is the formula for flux linked with the coil? Flux linked with the coil is nothing but ban cos theta, where theta is the angle between B and A. Theta is the angle between B and A. Yeah. Now, he said the field is perpendicular to the plane. He said field is perpendicular to the plane, clearly said. And we know that area is perpendicular to the plane. Field is perpendicular to the plane. Area is perpendicular to the plane. Both are like this. So that's why this angle cos theta, theta will become 0. Theta will become 0. Yeah, field is perpendicular to the plane. Area is perpendicular to the plane. The angle is 0. And cos 0, 1. So the first point here is that magnetic flux linked with the coil is ban cos theta. Since theta is 0, it comes out to be a simple ban. Simple ban. So already we know flux is ban. As per the question, I have to understand that this particular B is changing. That's why he is asking rate of change of B. So this B is changing. Understood? Area of the coil. Area of the coil is given as pi r square. Area of the coil is pi r square there. So area of the coil is pi r square. That is constant. The number of turns is constant. I am rounding it off. Rounding it off means constant. But since B changes, flux is changing, and he is asking what is the rate of change of B? Rate of change of B. Okay. Faraday's law. The EMF induced is nothing but the mod of d phi by dt. So phi means BAN. In place of phi, you have to write BAN. Phi is BAN from this one. So differentiation of BAN with respect to t. Here, you know that A and N are constant. The constant terms will come outside the differentiation. So AN constant into dB by dt. Point number 1. Okay, this is the EMF developed. Okay, EMF is the other name of potential difference. EMF is the potential difference. Okay, so whenever flux changes with respect to time, some EMF is induced, some current is induced, and naturally current is induced means some electrical energy developed as well as some power developed. Now, what is the power established in the question given there? P. Once again, from current electricity topic, you know that the electrical power is given by the three formulae, IV, I square R, or V square by R. The electrical power given by this one. That's what I was telling that time. You have to recollect a lot of fundamental formulae from other chapters of current electricity. Okay, EMF developed is nothing but V. You know V. And you know the resistance of the coil as R is. Resistance of the coil is given as R. When you know V and R, you can calculate the power. Power comes out to be V square by R. So power is V square by R. This V is nothing but PD. PD is nothing but EMF. So that's why E square by R. If you cross multiply, E square is PR. E is equal to root PR. And what is the EMF there? AN into dB by dt. Okay, AN into dB by dt is root PR. dB by dt is root PR by AN. And what is the area of each turn into pi r square? Because it's a circular coil of radius R. The cross-section area is nothing but pi r square. In place of A, you just write pi r square. Then in the next second, you will be getting the answer. Okay. The next question, please. Okay, sir? Yeah, here both question and answer are there. Once again, this has come in NTA conducted mains, but before that, it has already come in NEET. NEET PYQ, later in mains, not once, but 2 times there. So 3 times appeared question in the last 7-8 years. In a coil of resistance, the resistance of the coil is given as 100 ohms. Okay, in a coil of resistance 100 ohms, a current is induced by changing the magnetic flux. Yes, we started with that point only. Whenever flux changes, EMF is developed, current is developed. That's what he is telling. A current is induced by changing the flux. And how the current induced is varying with time means like this. Okay, whatever current is induced, that current is a variable current. The current is changing like this. As time changes from 0 to zero point 0.5 seconds, current is decreasing from 10 ampere. You can see from 10 ampere to 0 there, from here to here. So, in a coil of resistance 100 ohms, in a coil of resistance 100 ohms, by changing the flux, you are establishing current, and that current changes with respect to time like this. I want to know what is the change in the flux there, change in the flux. Okay. Now, coming to the first point there, all of you in the class know that whenever, already we discussed, whenever current time graph are given there, current time graph is given, area enclosed by current time graph will give you charge set into motion. Okay, this area enclosed by current time graph with respect to time axis will give you charge is set into motion. Charge set into motion is nothing but this area enclosed, this shaded area. Shaded area is nothing but area of the triangle. What is the area of the triangle? Half into base into height. Half into base 0.5, height is 10. Just simplify there. It comes to be 2.5 coulombs. This is a charge in a coulombs. That's a charge that is set into motion. Okay, now I want to know, he is not asking charge set into motion. What is the change in the flux? Already we discussed at the beginning of our class there that the charge set into motion is change in the flux by resistance. Yeah, if you go through the first page there, right in the first page, it is there, charge set into motion, change in the flux by resistance. Okay, from these things, change in the flux is nothing but charge set into motion to R. Charge set into motion is 2.5 coulombs. Resistance is given as 100. 2.5 into 100 will give you 250 Weber. So 250 Weber is answer for the bit. Yeah. A rectangular loop of length 2.5 meters and breadth or width 2 meters. So you can see that it is a rectangular plate like this. Suppose this palm is rectangular, for example. This is a rectangular one. The length is given as 2.5 meters. This is the breadth, 2 meters. Okay. A rectangular loop is of length 2.5 meter, breadth 2 meter. From that, what is the first thing we do? We calculate the area. Area is the product of length into breadth, 2.5 into 2, 5. The moment you know L and B, calculate the area of that rectangular strip there, 5 meters square. And area vector is always perpendicular to the plane. Yes, we discussed, perpendicular to the plane. So this is the area there. So this is the plane of this one, plane of this one. Area vector is perpendicular to the plane like this. This is the plane there. Area vector is perpendicular to the plane. Exactly like this. Okay, this particular one is kept in uniform magnetic field, okay, of 4 Tesla, making an angle 60 degrees. Okay, then what he says is that this this particular rectangular plate is initially in magnetic field. Now it is taken out of the field. It is initially inside the field, then you are taking it out there. How much time you have taken to take it out? 10 seconds. In 10 seconds, it is made to come out of the field. Now, I want to know how much average EMF is induced in the loop. Always average term you get when there is some time interval. Yes, there's a time interval of 10 seconds. Okay, for it to come out of the loop, it is we are taking 10 seconds to bring it out of the field there. Then in those 10 seconds, what is the average EMF induced? There's a question there. Okay, once again, our starting point you recollect. Flux is band cos theta. Yes, that is exactly the point. So flux is band cos theta. You know everything. B, you know, area, you know. Nothing is said means number of turns is 1. Yeah, number of turns is 1. And theta is given as 60 degrees. So everything is given there. Cos 60 is off. You get 10 Weber. Okay, this is the flux when the plate is in the magnetic field. When the plate is coming out of the magnetic field, There's no magnetic field at all. No magnetic field means B will become 0. Naturally, flux will become 0. Flux is band cos theta. B0 means flux is 0. That means here the flux is changing from 10 Weber to 0 Weber. You ask yourself, what is a change in the flux? What do you mean by change? Final minus initial, phi 2 minus phi 1. So phi 2 is 0, phi 1 is 10. So 0 minus 10 equal to minus 10 Weber. So change in the flux is minus 10 Weber in a span of 10 seconds. What is the average EMF induced? Instantaneous EMF means d phi by dt. Average means delta phi by delta t, we discussed. So average EMF induced is minus delta phi by delta t, minus. If delta phi comes out to be minus 10 by time. So minus into minus comes out to be plus. So the answer is plus 1 volts. Okay. Yeah. Now we are entering into the other concept of this topic, the self-inductance. Okay. Suppose there is a coil. There is a coil. This is the turn number 1, turn number 2. N number of turns are there. Okay, even in this next subtopic also, same beginning. So this is a turn number 1, turn number 2, turn number n. Okay, now through this particular coil there, let the current flowing through the coil is I. Okay, current flowing through the coil is I. Every one of us know from electromagnetism that whenever there is a current flowing through the coil, suppose the current in the coil is I, every current is developing some magnetic field. Every current establishes a magnetic field. Whenever there is magnetic field, there exists some magnetic flux. So through this particular coil of n number of turns, suppose the current is I, whenever current is there, there exists magnetic field. Whenever there is magnetic field, there exists magnetic flux. Now I want to know what is the flux linked with the coil. So flux linked with the coil is nothing but, the flux linked with the coil means the flux linked with the entire coil. The flux linked with the entire coil is n times the flux linked with each turn of the coil. So there will be some flux linked with this turn. There will be some flux linked with this turn, some flux linked with this turn. So flux linked with the entire coil. From here to here, this is said to be coil. This is said to be each turn of the coil. So most of you definitely know the entire structure is the coil, whereas this is one turn of the coil. The flux linked with the entire coil is n times the flux linked with each turn of the coil, and that is given by self-inductance of the coil into current in the coil there. This flux linked with the coil. So we have a small point that phi is directly proportional to I. Proportional is replaced by constant L. So flux linked with the coil is self-inductance of the coil into current through the coil. Okay, so for the last time I repeat. Whenever a current I flows through a coil of n number of turns, the total flux linked with the entire coil is n times the flux linked with each turn. Each turn will have some flux. So one turn will have some flux. 2 turns means 2 times, 3 turns means 3 times, n turns means n times the flux linked with each turn. That is nothing but L into I of the coil. Okay, now if at all this current in the coil is changing, this current is not constant, but current is changing. As the current changes, flux will also change. As the flux changes, EMF is induced according to Faraday's law. So if the current is somehow made to change, as current in the coil changes, flux changes. Whenever flux changes, EMF is induced. Okay, what the EMF induced in the coil means minus d phi by dt. Okay, minus d phi by dt means you have to differentiate this phi there. When you differentiate phi, the constant term L will come outside there. So minus L di by dt. So EMF induced in the coil at any time t is minus L di by dt. Okay, what is the formula for current induced? Whenever EMF is induced, current is induced. Current induced in the coil is nothing but EMF induced by resistance. EMF induced divided by resistance. Okay, that point you know from current electricity we already used there. Okay, the unit of the self-inductance you must be knowing as Henry. Okay, see here. Now, after self-induction there, we just enter into a little bit of mutual induction and do the questions related to both self and mutual inductions there. Listen, whenever you are talking about self-inductance, there will be only one coil. Is self means only one. Mutual means two. Is mutual help means A helps B and B in turn helps A. So there is mutual, as you know there. So we are talking about mutual induction. Right in this particular mutual induction, there will be two coils there. One particular coil that is being connected to the battery is called as a primary coil. The other coil is not connected to the battery, but it is connected with a galvanometer to record the current. Okay, then that particular coil is known as secondary coil. For the last time I repeat, that particular coil through which a current is being supplied is called as primary coil. The next coil is the secondary coil. Okay, every one of us must be knowing that whenever there is some current IP in the primary coil, let us say there is some current IP in the primary coil. Because of this current, there exists some magnetic field in the neighborhood. So because of this current in the primary coil, there exists a field in the field acting on the secondary coil. Because of the field on the secondary coil, there exists some flux there. That means there will be some flux in the secondary coil because of current flowing through primary coil. And the fundamental point which we have to frequently recollect is that flux linked with the secondary coil is M times the current flowing through the primary coil. For the last time I say, because of the current in primary, some flux is developed in secondary. So flux in secondary is M times the current in primary coil. M is known as mutual inductance. Okay, now if the current in the primary coil is changing, if the current in the primary coil changes, flux in secondary coil changes. Whenever flux changes, some EMF is induced, Faraday's law. So EMF induced in secondary coil is nothing but minus d phi by dt through secondary coil. And if you differentiate this one, it comes out to be minus m di by dt through primary coil. So EMF induced in the secondary coil is minus of M, mutual inductance between the two coils, into di by dt through the primary coil. So this is a small but important formula in the mutual inductance. And when once you know EMF induced there, we can calculate the current induced there. So current induced comes out to be EMF induced by resistance. So you know EMF induced and you know resistance there. From that you can calculate the current. So there's a first point place. Okay then, see here. Here comes this is a complete concept yielding question about mutual inductance there. Okay, when we are falling short of time there, 3-4 questions combination combined benefits we can get through a single bit like this and just concentrate on this bit. Yeah, there are a little bit of multiple concept in giving some good result. Now, when a current flows through a primary coil, okay, through a primary is that particular coil through which current flows is known as primary coil. When a current flows through a primary coil, you know that some field and flux are developed in the secondary coil. When current flows through a primary coil, a magnetic flux of 10 Weber is induced. A magnetic flux of 10 Weber is induced in that particular coil, in this particular coil of a self-inductance 20 Henry. Okay, this particular question is a ideal combination of self-inductance combination plus mutual inductance. Two things put together, two things put together. Okay, now I have written here clearly step 1. Okay, this is the step 1. You concentrate on the step 1. Okay, now in the step 1 there is a coil like this. There is a coil like this through which current is flowing. Okay, now when a current flows through a primary coil, a magnetic flux of 10 Weber is induced in this coil of self-inductance 10 Henry. So there is a coil like this of self-inductance 20 Henry. This is a coil of self-inductance 20 Henry. Because of current flowing, okay, because of the current flowing, 10 Webers of flux is being developed. Okay. From these things, what is the inputs we can have? In the case of self-inductance, you know that flux linked with one particular coil is nothing but Li. Phi is equal to simple formula, very cute and simple formula, Li. Flux linked with the primary coil is nothing but self-inductance of primary coil into current through the primary coil. First step. You know, when a current, what is the flux linked with this particular primary coil means 10 Weber. Self-inductance of the coil is given as 20 Henry there. From that, you can calculate the current in the primary coil. Current in the primary coil exactly comes out to be half ampere. So, as far as this first statement is concerned, the purpose of giving this statement is to calculate what current is being associated with the primary coil initially. For the last time, I repeat, through this particular primary coil, the flux associated is 10 Weber and its self-inductance is 20 Henry. So flux linked with the primary is L of the primary into current of the primary there. From that, you calculate the current through the primary coil. Then concentrate on the second step. Because of the current flowing through this primary coil, some field and flux are being linked with the secondary coil. Okay, because of this particular current, some flux is linked with the secondary coil. What the flux linked with the secondary coil means, 40 Weber of flux is linked with the secondary coil. Okay, from the first the 4 lines data, you understood how much current is in the primary coil. Good. Then, because of this current, he's telling how much flux is being linked with the secondary coil. What is the purpose of giving this data there? You know the basic point in mutual inductance. From self-inductance concept, now you are going towards mutual inductance. Flux linked with the secondary coil is M times the current flowing through primary coil. How much flux is linked with the secondary coil? 40. Mutual inductance, we don't know. And our idea is to calculate it. And current in the primary coil is half. So most of you have understood why we calculated IP. Definitely there is an important point there. So from these things, mutual inductance between the two coils you can calculate, 80 Henry. Okay, now the next thing is, as I said, multiple concepts. If the charge flowing through the primary coil, now he is making some charge to flow through the primary coil, and that too, the charge is time dependent. Charge flowing through the primary coil is given as TQ plus T square plus T. I want to know what is the current induced in the secondary coil of resistance 10 ohms at this time. Okay. Now, through this primary coil, charge flowing through the primary coil is given. Okay. Whenever the charge changes with respect to time, some current is being developed. I want to know what is the current in primary coil. Current in primary coil is nothing but dq by dt. Current in the primary coil is rate of flow of charge through the primary coil. So you have to do differentiation. Yes, in this topic, differentiation generally don't leave you. So differentiation of T cube is 3T squared, differentiation of T squared is 2T, this is 1. So this is the current in the primary coil. Okay. Now basically you want to know what is the EMF developed in the secondary coil. Already we have seen that the EMF developed in the secondary coil is nothing but minus M di by dt. EMF developed in the secondary coil is minus M di by dt. So, in order to calculate the EMF developed in the secondary coil, you have to know di by dt through the primary coil. That means rate of change of current through primary coil. Rate of change of current through primary coil. So, after calculating the current in primary coil, the next step is you have to calculate what is the rate of change of current through primary coil, di by dt through primary coil. Once again, you have to do differentiation. No other way. No second method for it. Impossible. Generally, many questions in physics can be done by many methods. But here, no second method exists, please. So the rate of change of current through the primary coil is, you differentiate it. So 60 plus 2 you get. Okay, this is a rate of change of current through the primary coil. What is the EMF in secondary coil? EMF in secondary coil, modulus, magnitude is M di by dt through primary coil. M already we have calculated 80. M we have calculated 80. Di by dt we got it as 60 plus 2. Okay, so this is the EMF developed in the secondary coil as a function of time t. He is asking what is the current induced and EMF induced at t is 2 seconds. So in place of this EMF induced, 80 into 60 plus 2, write t as 2, write t as 2. That's what we have done. We have written this 2. Then you calculate the EMF. That comes out to be 80 into 14. Don't multiply 80 into 14. Leave it like this. And I want to know what is the current established there at that time. Current is nothing but EMF by resistance. EMF by resistance, 80 into 14 by 10. So 8 into 14, it is 112 ampere. 112 ampere. Okay. In this particular topic, calculating the mutual inductance between two coils is always an important model. How to calculate mutual inductance? So they may ask you, within a square, another small square exists. Within a circular coil, another small circular coil exists, and so on. And these are the routine questions since decades. And the last 3-4 years, they changed the style. Okay, they started asking within a hexagonal coil, you have got a circular coil or a triangular coil, and then asking mutual inductance there. Now here is a simple version, simple possible question for the exam. Okay, now a square coil of side L, this is a square coil of side L, is kept concentrically in a big circular coil of radius r. There's a big circular coil of radius r and a small circular coil, because L is said to be very small than R. R is very large. R is very large. This is very small. That's what it says. A small circular coil is kept. Then I want to know what is the mutual inductance between the two coils. We want to know what is the mutual inductance between the two coils. I repeat again. Inside a big circular coil of radius capital R, a small circular coil of radius small r is kept concentrically. Both of them have the same center and of course coplanar in the same plane. Then I want to know what is the mutual inductance between them. Here you have to start with one particular step there. Here the method is important. Getting this particular point as the first point is a very important thing. Yeah, what does that mean, sir? Here, we have to assume. Generally, in any question, we don't do assumptions. Whatever the data they give, we use it. Okay? V is equal to U plus AT. They give U, AT. We calculate V. Where is the assumption? Nowhere we assume. Okay? But here, to calculate the mutual inductance, you have to first assume that this outer bigger coil as the primary coil. We are assuming the outer bigger coil as a primary coil, and primary coil is the particular coil through which current flows. Let us assume that let the current flowing through the primary coil is I there, and let us say that it is flowing in this anti-clockwise. Okay, let us say that let the current in the outer bigger coil is I, and let the current flow in anti-clockwise direction. Okay, now what you have to do as the first step is that because of this particular current flowing in the primary coil, I want to know what is the magnetic field developed at the center of this particular circular coil, nothing but at the location of the smaller coil. So because of the current flowing through the primary coil, you want to know what is the magnetic field induction developed at the center of the circular coil, where this chota sa, this small coil is being located. So the first thing is that be at the center of the circular coil due to this current there, IPC. All of you know from electromagnetism is this topic involves 2-3 chapters points being recollected. So whenever current flows through a circular coil, the magnetic field induction at the center is given by mu naught Ni by 2R, mu naught Ni by 2R. So B at the center of this one is mu naught Ni. I means current flowing through primary coil. R is the radius of this coil. So this comes to be mu naught. Unless said, we are talking about one particular turn there. So mu naught, number of turns comes to be 1, mu naught I by 2R. All of you know, when the current is clockwise, magnetic field is inward, anti-clockwise outward. This current is going anti-clockwise, this magnetic field is outward. So this is the magnetic field acting at the center of the circular coil, nothing but the outward field. Outward field is acting at the center of the circular coil as well as on the smaller coil. Okay, when the magnetic field is passing through the smaller coil, I want to know what is the flux associated with the smaller coil. Once again, we are going back to the point number 1 with which we started. How many times we use that particular formula? Just make a note, please. So the flux linked with this secondary coil, when this is the primary coil, naturally this happens to be the secondary coil. This is primary means this is secondary. So flux linked with the secondary coil is nothing but flux formula, ban cos theta, ban cos theta. So ban cos theta. But flux linked with the secondary coil means with care, your teacher has written BS, B acting on secondary coil, area of secondary coil, number of turns of secondary coil, cos theta. You remember that theta is angle between vector A and vector B, vector A and vector B. Yes, we discussed. Now, what the B acting on secondary coil means? Already we know mu naught I by 2R. There's a B acting on this coil, mu naught I by 2R, into area of the secondary coil. Area of secondary coil means area of this square coil. What is the area of the square coil of side L means L square. Side into side L square. So you have written B, you have written A. Number of turns, unless said the number of turns is 1. If they by chance they say n, a small n number of turns, you have to take that n. So nothing is said means n is 1. Theta is the angle between B and A. Already we know that for this, we are assuming that the current is in anti-clockwise direction. When the current is anti-clockwise, magnetic field is outward. Magnetic field is outward, area vector is also outward. Magnetic field is outward, area vector is outward. Both are out and out. That means they are in the same direction. Same direction means angle between them is 0. So cos theta means that theta comes out to be 0, cos 0. So the flux linked with the secondary coil is ban cos theta. From that, write carefully B, area. Area is square coil L square. Number of turns, unless said 1, theta is 0. Now, what is the fundamental point of flux linked with the secondary coil? You know that in mutual inductance topic, flux linked with the secondary coil is M times the current flowing through the primary coil. Okay, how we are calculating mutual inductance means by using this simple formula. Flux linked with the secondary coil is M times the current flowing through primary coil. So that point comes as the next step. So flux linked with the secondary coil is M times the current flowing through primary coil. Current flowing through primary coil is I. This I naturally get cancelled. So what the mutual inductance means? Mu naught L square by 2R. So what I want to tell you is, most of you are definitely thorough with square coils. Inside a big square coil, small square coil. Inside a big circular coil, small circular coil. But we need to be ready to face a simple question on the very similar lines with the square coil being kept inside a circular coil there. Okay, so this is a good answer for this particular question. So as we expect as teachers there, definitely you are using the time 100% effectively there. So our best wishes are always with you. All the best, my dear students. Okay, tomorrow we meet again with another topic. Bye-bye.